So first, before we start, for our viewers' sake, I really want to understand how is it that these quantum computers can do so much computation in so little time that they're threat to the crypto algorithms of today. Like, what is different between qubits and what is different in the conventional processors?
Let's get into this. See, conventionally we use either optic-based or magnetic-based storage or computing systems, right? Where small magnetic domains, you have spin like south and north. Okay, so if the magnetic domains are aligned towards north, then that is read as one. If it is towards south, then it is interpreted as zero. Right now, same goes with any other system. If you want to tap into EM waves, electronic or magnetic waves, impulse. So crusts are taken as one and troughs are taken as zero, right? So any of these conventional systems, they exist in binary, either one or zero, right? Now, quantum state. Now, when you have these semiconductors, etc., when you put them into cryogenic environment and super cool them, okay, and they become superconductors, right? Then between the molecular spaces, you have qubits. Okay, now particularity of these qubits are they have spin. Okay, so they are always spinning, right? And at any given point of time, you cannot exactly determine. You can sieve out a state, but they exist in both the states, plus and minus. Okay, now suppose you want to guess a number, okay, and you have 2 bits. From 2 bits, practically how many numbers you can have? 0 to 3, right? 0 0 0 1 1 0 1 1, right? Now you have to guess a number which is 4, and you are sorry 3, and you are starting from 0 0. You see whether that's the number that you want to match. So we want to match 3. Okay, so I have 2 bits, then I have to do 4 processing cycles. Okay, first I have to match 0 0 whether it is the number that I'm looking for. No, then do 0 1, then do 1 0, and then you do 1 1, and then you get the final result. Okay, this is the bit I was looking for, right? So you have to do 4 processing cycles. You have to 4 times load the data, unload the data, or flip the data, right? And then you compare. Now, if you have 2 qubits, both are presenting both the states. Okay, so at the same time, at one processing cycle, you can get the value 4, then that is 1 1, that denotes 3 in binary, and you got the answer. Or you can sieve it out that this is the value. Okay, you just XOR it and you get that 1 1 is the 0. You will get 0 0 if that value, both the values are common, right? So in this way, you can, in one processing cycle, you can get what should be the desired output, right? So now if you increase the number of the bits, then within very, very less manageable cycles, you can guess very, very big numbers, right? Now with this, you cannot brute force private keys directly. First of all, you need public keys as an input, right, to guess the private keys, right? So typically RSA, when we are talking about using quantum computers to break it, okay, you cannot guess the private key directly. It is still a big thing. Okay, what we have are certain algorithms for factorizing public key. So public key in RSA system, what is private key is you have two prime numbers, large prime numbers P and Q. Product of that is part of public key, right? If you have that product, challenge is because public key has to be made public. Okay, you have to give it to others so that whatever I encrypt with my private key, which is secret, others can verify using my public key, right? That's how you can authenticate that I have given this data. Right? So public key has to be given out. Now you have this product P and Q as public part of public key available with everyone, right? Now people are free to take that, run into some quantum systems, some algorithms, and then break it. Means factorize it. You can separate out the P and Q, right? Now that can be efficiently done with some algorithms, right? Those are very, very simple algorithms. Okay, uh, for few numbers you can do it by hand. Okay, Satyam can explain that very, very well. Okay, but now when you put that algorithms on quantum computers, then very easily you can break the systems. Of course, there are some nuances to that. Satyam is an expert on that. He can talk about it. Okay, so by and large, this is the idea that with factorizing algorithms, putting it on quantum computers, you can easily break the big numbers.